Bismillahirrahmanirrahim, starting with the glorious name of Almighty Allah. Today we are starting our physical chemistry first chapter, which is about stoichiometry. In this chapter we will discuss about the calculations regarding mole and Avogadro numbers, the limiting and excess reactants, and the theoretical yield, actual yield and percent yield, which is related to the mole concept or stoichiometry of a chemical equation. Then first of all we are going to discuss about the introduction of the stoichiometry. Stoichiometry is mostly used in chemical industries to calculate the actual amount of the substance which is actually participating in a chemical reaction. So first we will define about the stoichiometry. The study of relative amount of substance involved in a chemical reaction is called stoichiometry. How many reactants are utilized in a particular reaction, in a particular balanced chemical reaction, and how many products are formed. These amounts are actually calculated in a stoichiometric calculations, and this is all about the stoichiometry, in which we are going to calculate the amount of reactants which are actually participating and to produce a desired amount of product in a chemical reaction in a balanced chemical equation. It's the definition regarding stoichiometry. Now we will discuss further things. First we are going to discuss about the mole. Mole is an amount of substance. 1 mole of any atom is equal to the molar mass of that atom or molecule. Like the atomic mass, formula mass, and the molecular mass of a substance which is expressed in grams is known as a mole. 1 mole of any atom, any molecule, or any ion is equal to the molecular mass or the formula mass or the atomic mass of that element, compound, or a molecule. Like 1 mole of oxygen is equal to 16 gram, which is equal to the atomic mass of oxygen atom. Like 1 mole of water, water contains 18 gram. Its atomic mass is 18 mu, so its 1 mole is equal to the atomic mass of that atom, molecule, or a formula unit. Avogadro number, it's the experimentally defined value, or is a numerical value which is experimentally calculated in STP conditions, and standard temperature and pressure is considered there, and the number of atoms, ions, or molecules which is present in 1 mole of the substance actually is called the Avogadro number. Avogadro number is a fixed value which is equal to 6.022 multiplied by 10 to the power 28, 23 atoms, molecules, or ions. 1 mole of any gas at standard temperature and pressure is equal to contains 22.414 dm cube volume and 6.022 multiplied by 10 to the power 23 particles. Avogadro number is expressed in terms of capital NA. Okay. According to the equation, we can calculate the Avogadro number for different atoms or molecules. Like in the above equation, 2 hydrogen gas or plus 1 oxygen molecule is going to react and form 2 water molecules. So here 2 moles of hydrogen are utilized here, so we multiply 2 by Avogadro number, which is the fixed amount of value, 6.022 multiplied by 10 to the power 23. Okay, and above equation we have 1 mole of oxygen gas, so its Avogadro is equal to the Avogadro number. We don't need to multiply with any other number because it contains 1 mole, and the product which is formed is 2 mole of water molecule, so we also multiply 2 by Avogadro number to actually calculate the molecule of water. 1 mole of any atom is equal to Avogadro number. 1 mole of oxygen atom is equal to Avogadro number of atoms. 1 mole of oxygen molecule is equal to Avogadro number of molecules, and 1 mole of water molecule, which is also molecule, is equal to that molecules and Avogadro number. 1 mole of NaCl, like it's an ionic compound, contains Avogadro number of formula units. So the units are a little bit different, but the thing which is the actual amount is retained here, which is Avogadro number. Mole ratios. Mole ratio means the ratio of number of moles of reactant which are taking part in a chemical reaction. Is the ratio between the number of reactants by number of products which are formed is called mole ratio. Like combustion of propane, combustion takes place in the presence of oxygen. Complete combustion takes place in the presence of excess oxygen to form carbon dioxide and water molecules. So it's the equation of combustion of propane. The mole ratio between reactant and products. We have to compare the mole ratio between reactants and products. Like 1 mole of propane is going to react with 5 moles of oxygen molecule to form 3 moles of carbon dioxide gas and 4 mole of water molecules. Then we are going to calculate the mole ratio between reactants and products. Examples given there, so we can easily check what's going on. This methanol burns according to the following equation. Here methanol is burned in the presence of oxygen. 2 moles of ethanol molecules are going to react with 3 moles of oxygen molecule to form 2 moles of carbon dioxide and 4 moles of water molecule. In the above equation, 3.50 moles of methanol are given. So we have to calculate the number of moles of oxygen and number of moles of water molecules which are produced in above chemical reaction. First, the things which are given, we have to write about them. Moles of methanol is equal to 3.50 moles. Now we have to find the moles of oxygen. So first we have to check the ratios between which are given in the above chemical reaction. If 2 moles of methanol react, then 3 moles of oxygen must react. So 2 moles of methanol is equal to 3 moles of oxygen. First we have to write the mole equation according to the above balanced chemical equation. Then if we are going to react 1 mole of methanol, then how many moles of oxygen will be utilized? It's 3 divided by 2. Then if 3.5 moles are given of methanol are going to react, then how many moles of oxygen will react? 3.50 multiplied by 3 by 2. So 5.25 moles of oxygen are going to react in the above chemical equation. Now number of moles of methanol are already given. We have to find the number of moles of water molecule. Now we have to again check the if 2 moles of methanol are going to react, then 4 mole of water is produced. It means it's going to double. So 2 moles of methanol produce 4 mole of water molecule. 1 mole of methanol will produce 2 mole of water molecules. Then if 3.5 moles are there, so we just going to multiply or double the value to calculate the number of moles of water molecule which are produced in a chemical equation. If we multiply 3.5 by 2, then we got the answer. 7 moles of water molecules are actually produced in the above chemical reaction. Now the self-check exercise 1.1 is same as the above. In this exercise, the ammonia production is formed here. Actually the nitrogen and hydrogen are going to react and form ammonia. Nitrogen contains 1 mole or 1:3. 3 moles of hydrogen are going to react and form 2 moles of ammonia. How many moles of the following are required to manufacture 5 moles of ammonia? So we have to calculate the number of moles of nitrogen and hydrogen respectively to form 5 moles of ammonia. So first we have to calculate the balanced chemical equation, mole concept. Then we can easily calculate by above example, like above equation. We just do it. Now we are going with another example that is little bit difficult than above. Iron can be produced from iron ore by reacting the ore with carbon monoxide. Carbon dioxide is produced in this reaction as a byproduct. What mass of iron can be formed? Now mole to mole calculations are stopped here. Now first we have to calculate the mole, then we have to calculate the mass. Actually, what mass of iron can be formed from 425 gram of iron ore? Here first of all we have to write the balanced chemical equation, or the balanced chemical equation is already given. So we have to notice that the balanced chemical equation is already there. Iron oxide plus 3 moles of carbon monoxide are going to react with 2 moles of iron plus 3 moles of carbon dioxide. The mass of iron ore is present here, which is 425 gram given mass. Number of moles of iron ore. First we have to find the number of moles of iron ore. The moles formula is mass divided by molecular mass or molar mass. The mass which is given is 425, and molar mass of the above Fe2O3 is We can easily calculate it by using atomic masses of oxygen and iron respectively, and which is 159.6 gram per mole. By taking the ratio of 425 to 159.6, we got the answer 2.66 moles. So moles of iron ore are present there. Now 1 mole of iron ore is going to form 2 moles of iron metal. So 2.66, if 2.66 moles of iron oxide are going to react, then it's going to double to 2.66 multiplied by 2. It's going to 5.32 moles of iron are formed actually. The moles of iron are formed there. Now we have to calculate the mass actually, mass of iron. So mass is equal to moles multiplied by molar mass. Moles are 5.32 and molar mass of iron is 55.9, which is approximately equal to 60 gram. By multiplying moles by its molar mass of iron, we got the mass of iron which is produced, which is 297.388 gram. So we can easily do it. First we have to calculate the moles from balanced chemical equation. Then moles are converted into mass by multiplying moles and molar mass. We can easily calculate the mass of that particular atom. Now self-check exercise 1.2 is similar. Here also we have to find the mass. The balanced chemical equation is given here. So we have to find the mass of oxygen. The mass of hydrogen is given there. So we can easily calculate it by above example we did. Calculate the number of mole of oxygen produced by thermal decomposition of 490 gram of KClO3. Potassium chlorate. Number of molecule of oxygen we have to find. First we have to write the balanced chemical equation, then we can easily solve each and everything. First the things which are given are the given mass of potassium chlorate, which is 490 gram. Formula mass we have to calculate itself. We have to calculate KClO3 formula mass, or actual number of atoms which are present. The atomic mass of each atom is added up and we get 122.5 mole per gram per mole of formula mass of potassium chloride. Number of moles we have to find the number of moles by 490 divided by moles divided by mass divided by mass multiplied by number of moles. We have to find the mass divided by molar mass is the formula actual here. 490 divided by 122.5 करेंगे तो we get 4 moles. Now the moles are calculated. So first we have to write the balanced chemical equation. If potassium chloride is going to react, it form potassium chloride plus 3 moles of oxygen molecule. If 2 moles of potassium chloride are there, then 3 moles of oxygen is produced according to balanced chemical equation. Then if 4 moles of potassium chloride are present, then what is going to happen? 3 by 2 multiplied by 4. 3 by 2 multiplied by 4 is formed. Then 6 moles of oxygen are actually produced. If 1 mole of oxygen is equal to the contains the Avogadro number of molecules, then 6 mole of oxygen contains 6 multiplied by Avogadro number of molecules. So if we multiply 6 by Avogadro number, we get the molecules of the oxygen, which contains 6 moles of oxygen atoms. Now the above example is also like that. 20 gram of H2SO4 on dissolving in water ionizes completely. Calculate number of H2SO4 molecules, number of potassium, number of hydrogen and sulfite ions, mass of individual ion. We have to find the number of H2SO4 molecules, then we have to find the number of cation, which is proton or sulfite ion, anion, mass of individual ion. We have to calculate all three things. First, mass of H2SO4 is given, or we can calculate it. It's 20 gram. Molar mass, we can easily calculate the molar mass of H2SO4, which is 98.016 gram per mole. Number of molecules, if we are going to find the number of molecules, then we have to actually mass divided by molar mass multiplied by Avogadro number. 20 divided by 98.016 multiplied by 6.022 multiplied by 10 to the power 23. We get the 1.228 multiplied by 10 to the power 23 number of molecules of H2SO4 containing 20 gram of mass. H2SO4 dissolve in water. When H2SO4 dissolve in water, it ionizes and forms cation and anion respectively. Two H positive ions are formed and one sulfite ion is formed. According to the equation, 1 mole of H2SO4 will produce 2 mole of H positive ions. Then one molecule of H2SO4 contains 1.228 multiplied by 10 to the power 23 molecules of H2SO4. Then we are just going to multiply it a value by 2 to get the 2 H positive ions concentration or molecules. 1 mole of H2SO4 is going to form 1 sulfite ion according to the above balanced chemical equation. Then it also contains 1.228 multiplied by 10 to the power 23 number of ions, sulfite ions. Mass of individual ion, we can easily calculate the mass of individual ion by number of ions divided by Avogadro number multiplied by molar mass of that ion. Like we are going to calculate the mass of H positive ion, as number of ions which are formed is 2.456 multiplied by 10 to the power 23. We can divide it with Avogadro number multiplied by its molar mass 1.008, its molar mass of H positive ion. So we can easily calculate it in gram. 0.411 gram is the mass of H positive ion, and we can easily calculate the mass of sulfite ion. The formula is same. Mass of sulfite ion, which is 1.228 multiplied by 10 to the power 23, divided by 6.022 multiplied by 10 to the power 23 multiplied by 9.68 is the molar mass of that ion, sulfite ion. It's going to be 19.58 gram mass of sulfite ion is calculated here. What's the molar volume? Molar volume is the volume which is present at the standard temperature and pressure conditions. We call it STP. 1 mole of any gas contain 22.414 decimeter cube or dm cube of volume. This volume is known as molar volume. 1 mole of any substance or any gas contains that volume. And it's equal to the Avogadro number. Like the examples are given there. 1 mole is equal to 22.414 decimeter cube of any gas at STP. The gas may be hydrogen, the gas may be ammonia, or the gas may be carbon dioxide or other gas like. Okay, the 1 mole contains the atomic mass of that particular molecule. Like hydrogen gas contains 2 gram and ammonia gas contains the atomic mass of 17 gram. So the things remain the same, like the molar volume and the Avogadro number remains the same because it's equal to the 1 mole. Now we are going to discuss the example 1.5, which is about the molar volume. Determine the volume that 2.5 moles of chlorine molecules occupy at STP. Now we know that 1 mole of any molecule contains 22.414 dm cube of volume. So if 2.5 moles are there, so we simply multiply 2.5 by 22.414 to get the actual volume which is present at standard temperature and pressure. Okay, now we did like that. 1 mole is equal to 22.414. So if 2.4 moles are present, so we simply multiply 22.414 dm cube by 2.5 to get the 56.035 dm cube of the molar volume. Now going towards self-check exercise 1.3, which is also about the molar volume, so you can do it. Percentage composition. Now we are going to check the percentage composition of a particular atom or a compound in a chemical equation. The relative amount of each element in a compound are expressed as a percentage composition. The percentage composition by mass in magnesium oxide. To determine the percentage composition of a noun compound, first we have to calculate the molar mass of that compound, then the percentage of each element present in 1 mole of that compound. This is done by dividing the mass of each element in 1 mole of the compound by the molar mass multiplied by 100. If we are going to calculate the percentage of an element which is present in a particular compound, so we have to calculate the mass of a molar mass of that compound or mass of that compound in 1 mole of a substance divided by molar mass of the compound multiplied by 100. So we can easily calculate the percentage of that compound. There are two types of reactants, limiting and non-limiting reactants. The non-limiting reactants are also called excess reactants. Limiting reactant which is consumed completely in a chemical reaction. which is present in least amount, so it is easily consumed or completely consumed and readily consumed in a chemical reaction which produces least amount of product. It is also defined as a reactant which produces the least amount of number of moles of product in a chemical reaction. The reactant which is left unused or which is not completely consumed in a chemical reaction is known as non-limiting reactant, or excess reactant which is not completely consumed in a particular reaction, chemical reaction. How we can calculate or identify limiting reactant in a particular chemical reaction? Limiting reactant, we can easily recognize the limiting reactant by calculating the number of moles of product, and we can easily compare the reactants with each other, like which reactant is going to produce more product or less product, like this, using a balanced chemical equation. The reactant which produces the least number of molecules or least number of product is called the limiting reactant. 10 mole of hydrogen and 7 mole of oxygen were reacted to produce water. Which one of the if 10 mole of hydrogen and 7 mole of oxygen were reacted to produce water, which one of the reactant is the limiting reactant? So we can calculate it stoichiometrically, or from balanced chemical equation we can easily calculate, and then we can tell which is the limiting reactant or which is not. Two hydrogen gas molecules produce 2 water molecules, so 2 moles of hydrogen will produce 2 moles of water molecule. If 10 moles of hydrogen gas molecules are present, then 10 moles of water molecules are also going to present. Now second, we have to calculate the oxygen molecule with water molecules. If 1 mole of oxygen is present, then 2 mole of water molecules are formed. If 7 moles of oxygen are present, then 2 multiplied by 7 is equal to 14 moles of oxygen are formed. Then it means hydrogen gives the least number of moles of water. Hydrogen is given 10 moles, otherwise the oxygen is giving the 14 moles of water molecule. So hydrogen is giving the less number of moles of water molecules, so hydrogen is the limiting reactant in the above chemical equation, and the other oxygen molecules the excess reactant or non-limiting reactant. So like this we can calculate the limiting reactant. Okay, the other examples are also there, you can also check it and understand it. Okay, now we are going to discuss amount of reactant present excess in a chemical reaction. During a chemical reaction in which two reactants are reacted sometime, one component is consumed completely, which is called the limiting reactant, and the other component or other reactant is left unreacted. The reactant which is consumed completely during the chemical reaction is called limiting reactant, and the other reactant whose amount is left unreacted or which is not completely utilized in a chemical reaction is called reactant in excess. Okay, so the most important topic in the above lecture is theoretical yield, actual yield, and percent yield, which is more much important. So we are going to discuss it. The quantity of the product calculated from if we are going to calculate the amount of a substance from a balanced chemical equation, then it's known as the theoretical yield. If we are going to experimentally determine the amount of the substance which is actually produced in a chemical reaction experimentally, then it's called actual yield. The quantity of the product that is actually produced in a chemical reaction is called actual yield. The percent yield can be calculated by percent yield is equal to actual yield divided by theoretical yield multiplied by 100. Its formula is like that. There are many reactions in which the actual yield is almost. There are so many reactions in which the actual yield and theoretical yields are almost equal. Such reactions are quantitative, like chemical indices takes place in these reactions. On the other hand, some reactions, particularly those organic compound reactions in which the actual yields are